Okay, we have discussed indicator solutions. We discussed buffer solutions. Last piece for us in this unit on acids and bases is titration. We originally introduced the idea of titration actually back in December when we talked about analytical techniques in general. So ways to find the concentration of an unknown of a solution when you don't know the concentration of that solution. We introduced gravimetric analysis at that point. We did spectroscopy, so visible spectroscopy. If you have a colored solution, you can find the concentration by spectroscopy. And titration was the third technique we introduced. So with acids and bases, this is one kind of titration. In general, the idea is this. You have an acid plus a base reaction. And you do a reaction where the products doesn't really matter. But the key to titration is that you know the concentration of one of them and you don't know the concentration of the other. So you could either do titration where the acid is known and the base is unknown, or you could do the titration where the acid is unknown and you know the base concentration. Now the key to any titration is you need to have some sort of visible change or some sort of observable change. It doesn't have to actually be visible. But there must be an observable change when the number of moles of each reactant are equal. Now for many titrations, that change is a color change. That's often what you observe. With acids and bases, we could actually make it have a color change at that point. But there's also going to be another observable change, and that's going to be a change in pH. So that's what we're going to explore today. What happens to pH during a titration? Okay. The setup for a titration, we did one last week, so this shouldn't be unfamiliar. But you have a burette containing base or acid, and this is where you put your solution of known concentration. And we have a name for that solution that's up there. We call this the titrant. And then there's the solution at the bottom that has unknown concentration. That's the one we're trying to analyze. So we call it the analyte. So as you saw last week, you add small amounts of the titrant at a time until you reach that observable change. And we call that the endpoint of the titration. So last week, what was the change we were looking for in the lab? Color change. We had put an indicator solution in the analyte, and we saw that when we reached that equivalence point, it either went from clear to purple or from purple to clear. All right, so today we're going to try and explain why does the indicator change at that point? How do we know it's going to change at that point? What's going on with the pH during the titration? Okay. So I'm actually going to skip over the strong acid, strong base part because it's less interesting and it's a simpler part. So I'm actually just going to post last year's version of that. Sorry? So the response was, does that mean we have to watch it at home? It's available for you to watch. You may, after seeing today's, what we do today, you maybe just look at the notes from this part and say, oh, okay, that makes sense. All right? Because it's actually a less complicated example of what we're doing today. So we're actually gonna skip over the strong acid, strong base titration, and we're going to talk about a weak acid, weak base titration. So what we'll do is we're going to imagine we're doing a titration where HF solution is our analyte. I'm telling you what the concentration actually is, even though in a normal titration you wouldn't know what the concentration of the analyte is. I'm telling you what it is so we can follow what would happen to the pH over the course of the titration. And then we can apply that to situations where we didn't know the concentration. So our analyte in our titration is going to be 0.2 molar HF solution. And then the titrant is going to be NaOH. And I want you to ignore the fact that I've only put one sig fig on all my numbers here. Let's pretend these are exact values. So we're not going to limit the significant figures. All right, so this first slide, if I start with 50 milliliters of 0.2 molar HF solution, what's the original pH? You all can do that calculation right now. I know you guys are good at this because you did it very well in the quiz. So start with that calculation. I'll do it myself. All right, looking around, looks like most people made their ice chart, did the solution. I used the negligible X approximation. Did anyone not make that approximation? So I made the approximation that 0.2 minus X was roughly equal to 0.2. This is one of those borderline cases. If I go back and check my value of X at the end, I always like to go back and check. So is 0.2 minus 0.012 roughly equal to 0.2? It's going to depend on your application. It's going to depend on, you know, what your error tolerance is. For me, this is good enough because we're just trying to get an idea. No. Right. So since this is 7.2 times 10 to the negative 4, it's in that borderline area. And we see, you know, this is 0.188. And so the question is that close enough for you or not? And it all depends on what situation you're dealing with. If you're an actual chemist and you really have low tolerance for difference in pH in a particular application, then you'd say, all right, I need to actually solve this out. But if you're just us and you're trying to get an idea of what happens to pH during a titration, then this is good enough. Yeah. So the student question is that the same for the AP test? Would that be acceptable? My response is, I have not seen an example where you had to solve a quadratic equation. So, yeah, my guess is they probably wouldn't put you in this borderline area. They might use a slightly weaker acid with a lower Ka. But you're probably going to be making the approximation. All right, so the student question is, will we get a list of Kas and Kbs on the AP test? You don't get one, like a standard one, like we've given you. So any values that you need have to be given somewhere in the question. So it does make it a little simpler because, you know, we'll ask you a little more open-ended questions, knowing that you can look things up. There you'll know if it's asking me to do something where I need a given Ka, it has to be given. So that also tells you if the Ka is not given in the question, then you don't need it. Yeah. All right. So now we ask the question, what if I start with my 50 milliliters of 0.2 molar HF solution and I start adding my titrant? After I've added 5 milliliters of titrant, what is the pH of the solution going to be? Turns out this is a much more complicated question. One main reason it's more complicated, I start with 50 milliliters. I've added 5 milliliters. So my volume has changed. So even if I just added 5 milliliters of water, the concentration would change and the pH would change because of it. So when I do my charts for this kind of problem, because the volume is changing, I'm going to do my charts in moles, and then I have to divide by the new total volume at the end to get concentration again. All right? So this is a key difference from basically all the problems we've done to this point. And actually, I'm going to do something else that makes things a little easier for me, but some of you might not like it. Because I'm dealing with small numbers of moles, right? 5 milliliters is 0.005 liters. And I have 0.2 molar. If I multiply those together, I'm going to get, a really small number of moles, 0.0001. So I'm actually going to work in millimoles instead of moles, just so that my numbers aren't tiny decimals. Millimoles is just MMOL. So the first thing we need to ask ourselves before we can solve this question is, what reaction am I going to write? When I write a rice chart, the R stands for reaction. So what reaction am I actually going to write out? All right, I have HF plus NaOH. Those are my two reactants. Except NaOH, I really want you to get into this habit. When you see NaOH, what should you do? Get rid of the Na plus, because that's always a spectator. So I'm just going to make this OH minus. So my reaction is going to be HF reacting with OH minus. What are those two things going to make? What are they going to make? H2O and F minus. All right, that's going to be the reaction that I write. So my next question is, I need to know a K value. Because what K value I have is going to determine whether I do a rice chart, send the reaction to completion. So I need to know the K value. So think for a moment, talk to each other at your table. What is the K value for this? Or how would I find the K value? "30 seconds for discussion." Separate. All right. So what is the clue here as to what kind of K value I'm dealing with. All right. I see OH minus in it. As soon as you see OH minus in the equation, that should tell you, oh, that's a base. I should be thinking it's kind of a KB. But OH minus in a KB equation is a product. Here, since it's a reactant, this is the reverse of a KB equation. Right? So it's the reverse of KB for what base? Not OH minus, because OH minus is always in every KB equation. It's not HF, because HF is not a base. Not H2O. There's only one thing left. F minus. This is the reverse of the KB for F minus. Right? This is why we practiced on problem set 17, writing the chemical equation for what corresponds to KB of something or Ka of something. This is the reverse of KB for F minus. All right. So K is going to equal 1 over the KB of F minus. So now you look at your KB list, and of course, you don't find F minus. All right. So how would I get the KB of F minus? All right, I know that KB of F minus times Ka of HF has to equal Kw. And so Kb of F minus will equal Kw over the Ka of HF. So now I know that K for the reaction I'm looking at is going to be the reciprocal of that. All right, so students jumping to the conclusion, already seeing this is going to be a big K value. Why does your instinct tell you it's going to be a big K value? Okay. What do you know about the value of Kw? All right. Kw is a really small value. So when I divide by that, I'm going to get a big value. And if you just plug in the numbers, K is now going to be, what is it, 7.2 times 10 to the negative fourth divided by 1 times 10 to the negative 14th. So now I get 7.2 times 10 to the positive 10. Can we all agree that's a big K value? Huge K value. So since it's a big K value, we know it's going to do what? Go to completion. And part of what you'll do on problem set 19, if you haven't started it, I strongly encourage you to, but if you haven't started it, the first half of it is really proving to yourself this idea that when you mix an acid and a base, the K value for that reaction between them is always really big. Those reactions always go to completion. So I know what reaction I'm going to write, and I know to send it to completion. So let's do that. Now, I said earlier that we're changing volume. So since we're changing volume, I'm going to do the rice chart in millimoles in this case. And here's why I'm going to use millimoles. Because if I take moles per liter and I just multiply by milliliters, it'll equal millimoles. So this will allow me not to convert all my volumes into liters. Just use them in milliliters. And so then, in the end, when I want to convert back to concentration, I can also use the relationship that millimoles divided by milliliters equals moles per liter, right? So it's just going to save me some steps. It's going to save me from writing really small decimals. So to fill in my initial values, I go back here and I have 50 milliliters, 0.2 molar HF solution. So not initial concentration of HF, initial number of moles of HF. To find that, I would do just 50 milliliters times 0.2 moles per liter. And that gives me what, 10 millimoles. So I can just fill in 10 here. All right, now for OH minus. There I had, what, 5 milliliters? So how many millimoles is that? 1. So I can put a 1 there. All right, this is going to go to completion, so I need to identify what's my limiting reactant. So 10 millimoles versus 1 millimole, I'm going to run out of the 1. So OH minus is limiting. So this will be -1, this will be -1. Oh, I forgot on the right-hand side. We start with 0, F minus, and now we have +1 of that. Now remember, I can't have 0 of anything at equilibrium, so I've got to send it back a little bit. And if you don't want to write out this extra step, you don't really have to. You can just tell yourself, okay, anytime there's a 0, I know it can't be a 0, so I'm going to turn it into an x. Because that's essentially what happens. And at this point, you actually do have a couple of options for how to find the pH. One would be, notice I have a certain amount of HF and a certain amount of F minus. What's the relationship between those two? What do we call HF and F minus? What's the relationship? They're a conjugate pair. Anytime I have known amounts of a conjugate pair, I can take the shortcut like we did last week and use that HH equation. You know, we did it here, for example. Not there. We said you can stop there at the completion step, use the HH equation, and that's perfectly valid. Or you could use the equilibrium expression now. If I'm going to use the equilibrium expression, I need to convert my millimoles back into concentrations. So to get concentration of HF, that's going to be 9 millimoles divided by, what's my new total volume? 55 milliliters. And concentration of F minus is going to be 1 millimole divided by 55 milliliters. So the reason it's 55 milliliters is I had 50 and I added 5. So what's 9 divided by 55? 0.164. 1 divided by 55. So I could set up the equilibrium expression. K equals concentration of F minus over HF times OH minus. So I know that's equal to 7.2 times 10 to the 10th. So X is going to be very small. What is it? All right, X represents what here? Concentration of OH minus. So the POH would be the negative log of X. that's going to be 11 point. So then the pH will be 14 minus that, which is 2.18. So again, I'll point out, I solved this the long way. We could have stopped right here at the completion step and done the HH equation. So for the next one, we'll do that approach. The one reason I like to do this approach is going to work for every step in the process. The HH equation will not work when we reach a certain point. All right, so we started at 1.92, went up to 2.18. So the pH is going up slowly. If you actually flip ahead, we can fill in these values. Because in the end, we're going to make a graph of what happens. All right, so the next calculation, we want to do the same calculation now for after 25 milliliters of NaOH has been added. So take a minute now that you've seen the technique. We know what reaction we're looking at. We know that it's going to go to completion. So write that out, and I'll do the same. There's a lot of students in the room who are wondering why the screen went blank. Well, they were supposed to be doing it themselves. So I'm done. Is it? Maybe. Hmm. All right, based on the chatter, I'm going to assume those who are doing it themselves have finished. Um, so, same chart. I'm going to send it to completion. I'm still starting with the same number of moles of HF. I've just added more OH minus. And when I get to completion, well, OH minus was limiting again. So when I send it to completion, now I have 5 millimoles of each. We've seen this scenario before. I have equal concentrations of an acid and its conjugate base. When that's the case, the pH equals the pKa. I wrote out the HH equation up above, but the key is, since the two concentrations are the same, this second part of it equals 0. So the pH is going to equal the pKa, which turns out is 3.14. So I guess HF is like the pi acid. I don't know. Well, you guys are the ones who pointed it out to me. I've never even thought about it before. It's not 3.14159, but yeah. Maybe if we knew the Ka to more digits, it might match up with pi. I don't know. All right. So you get the idea. All right, the next one should be pretty simple. I'm going to go fill in my value here. After 25 milliliters, we're at 3.14. So now after 45 milliliters, you should be able to do this quickly and without watching me. Okay, at this point in my titration, I now have a pH of 4.1. The next one is where the magic is going to happen. So, go ahead and do the next one. Okay, what happened differently this time? There was no limiting reactant. They had equal numbers of moles. We have a special name for this point in the titration. This is called the equivalence point. So, when we reach the equivalence point, we run out of both of them. So now we send it back. We can't use the Henderson-Hasselbalch equation because we don't know the concentration of both members of the conjugate pair. So I have to send it back. All right. Now this is where it's important to remember that in an equilibrium expression, I must use concentration. So the tendency is to say, I'm going to set up my equilibrium expression to say K equals 10 over x squared. But that is not right. K is actually equal to 10 millimoles over how many milliliters? 100 milliliters divided by x squared. So 0.1 over x squared. And that K value is the same one we determined earlier, which was 7.2 times 10 to the 10th, I believe. So if you solve, all right, 1.18 times 10 to the negative 6th. So the POH is going to be the negative log of that. All right. So the very last thing before we go, and we'll pick up this thread tomorrow. If we look at our pH values, oops, wrong way. Look at our pH values to this point. Slowly increasing, slowly increasing, slowly increasing. Suddenly that last 5 milliliters, boom, the pH jumped up. That's going to be an observable change that will tell us we've reached the equivalence point in a titration. All right, we'll finish off this analysis tomorrow.